And so for the warm-up, I think the best, I have written, our textbook is based on my recent book, right? But I didn't have a appendix for linear algebra. The reason being I have written three books, all have the linear algebra background. They're all very good. The first one, right, there is an appendix with linear algebra. And that's my first book about 3D vision. And you can see that you get to learn the basics of linear, warming yourself up. Essentially, this is not to try to teach you linear algebra. It's for you to familiarize the notation we're going to mostly use, convention we're going to use in a series of work. And also some of the basic properties about, for example, linear algebra and concept, rank, range, and property of some matrix. Essentially for our use, for example, singular decomposition, PCA, and so on. This is by far the most important results. And there is a proof also given here. You can actually check, right? Some of the basic properties, geometric interpretations, and also we'll cover, and also you'll read the textbook on your own. I'm not going to, in a graduate course, we're not going to follow the textbooks team. So we're going to extract material to teach on lectures. So your job is to read the textbook. So by now you should have already read the first chapter, okay? Doesn't matter you understand it or not, you should be able to have already read it, at least try to read it. And also, of course, you can see there are a lot of covers, a lot of material be covered, right? Requires some background information. For example, there we mentioned Wiener filter, Kalman filters, right? So you will find that Appendix B, that all the least square, least estimation, Kalman filters, Wiener filters are fully derived here. And that's also the notes is given to you. And I'll cover that in today's lecture. And this is linear algebra and its applications to signal processing and control, some basic linear systems, signal processing and linear systems. And another thing is that for our textbook, right, we're going to use some of the information from the appendix as well. I think, for example, optimization, but we're not going to use the right way, but you are supposed to warm yourself up and some of the basic concepts. And Professor Wang Peng will give a lecture later about optimization, but yourself should familiarize with you. The more you're familiar with the notation, the convention, and remind yourself some of the techniques, some of the things you have learned from previous courses, the better, right? So you'll be able to follow the course, follow my lecture better. Okay, so that's the requirement. So, and so far you should also familiarize you with yourself with the Appendix A of the textbook, which is about the optimization, background, and or also my previous book also has information, appendix about the optimization as well, but they are covered slightly in different purposes, convex set functions, and for example, basic optimization problem, optimization condition, they have a different coverage because the topics are slightly different, right? So in our textbook, the coverage is more tailored to what we're going to use in our course. But nevertheless, the general background, the better you warm yourself up, the better, right? So those are in my previous book. There's also appendix. Take a look, right? Linear algebra, statistics, and also the optimization. Right? So I think this week the TA are working on the first homework and assignment. So you'll be forced to do some. Okay, let me get started with the lecture. Shoot, how do I get to access my, because this thing is, bar is a little bit crowded. Okay. Full screen mode. Okay, let's get started. The TA Chen Feng, and please remind me, I don't know, since I'm giving a lecture, I'm not sure, I don't get any reaction. Just in case you cannot hear me or I lose contact, or anything happened to the network, and please call me on my phone, right?
Okay, I'll do that.
Or remind me through Zoom, but if Zoom didn't work, just call me on my phone, all right?
Okay.
That's a protocol. Okay, good, just in case. All right, let's get started. All right, so this is lecture 2, right? The previous lecture, I think I gave a little bit of overview about what intelligence is, right? What this course is about, understanding the mathematical and computational principles and mechanism behind intelligence. In particular, of course, we try to understand what have been practiced in the past decade, right? Led by the deep networks, revolution, and so on. I gave a little bit coverage about the history, the overall picture, the intelligence we observe from nature, and also, of course, some of the recent years engineering practice, right? So the second lecture we try to, again, try to focus on the book, chapter 1, right? For anyone, we're going to try to, this semester, we're trying to follow the book reasonably closely. So usually the book is written in the following way. So we will read in each chapter is intended for 2 weeks teaching. So 2 weeks lectures. So roughly we will cover 1 chapter per 2 weeks, maximum 2.5. Okay, that's the pace we're going to do. So you guys should plan yourself in advance in terms of reading, in terms of preparing yourself. Okay. So this is the second lecture, roughly about the rest of the book. Chapter 1. So also this is the first couple lecture. There's some administrative matters. I want to repeat those a little bit because there's some new students joining and in the first couple weeks. And also there's Hetao AI School also has many students join. I'll just repeat this a little bit. And I'll be teaching, and Professor Wang Peng of Aumen Daxue, University of Macau, he will be our guest instructor, because at least by now I will be away for travel for September 2nd and October 20th. He will come to HKU and offer giving the guest lectures. And meanwhile, he will also be the assistant teacher for the Hetao. Probably go there on a regular basis, probably at least once per 2 weeks, and giving some lectures, discussion sessions, lead the discussion sections, and also answer questions. I will try to go to Hetao once in a while, but probably not on a regular basis. At HKU, there will be some teaching assistant, Tianze, Chenfeng, Siyan, will be the teaching assistant, help coordinating all the back-end foreground about the lectures and as well as the homework assignments. And we're still selecting some TAs at SLAE may help with the support. And also we're trying to plan, Peng and I probably also plan some office hours, mostly online. Probably HKU we can probably do in person, but we'll see. I'm still trying to get it, wait till my schedule gets settled. And also the book is online. It's open source book on the GitHub. So, well, if you cannot access GitHub, try to use VPN. So this is actually completely open source book. I think I talked about it. Many of you should be aware of it. By the way, this book is probably updated on if not a daily basis, on a weekly basis, as we're talking now, right? So you can see the last updated version is September 8th, as of today, right? Although the first version was released about 2 weeks ago, but it's being updated. So it's an open book. Everybody find anything you can just submit, corrections, typos, you can just submit to GitHub, just like open source softwares. So, and all the files are open sourced. And also there is also an AI helper as well. Tianze and someone are developing more tools, AI tools to help you to study teaching and research. Okay, so that to basically also, for most of you, I think the website is where you should visit it frequently. All the related resources is there. And also there's a Chinese version. If you look at pull down here, you actually have a entirely Chinese version. There's a website version, and also there's a PDF file, right? So this is, and also you can read the PDF and switch back to English as well, right? Right. So I'm back to my slides. Just tell me if I'm not. I'm switching to screens, but I don't know if exactly what you saw, but I hope this works. In terms of the main references, right, as I said, some of the, there's a book about slightly more heavy book for more analytical or theoretical oriented people. There's a book by me about a couple of years ago, high dimensional data analysis with low dimensional models. The book actually, the PDF is available. It's not as convenient as our current textbook, but there's a PDF file you can download from GitHub or Dropbox. And also that I also posted the appendix, right? The chapters that you will need to read. The grading is actually very simple. Homeworks will be 60%, then almost weekly written or programming homework, and will be assigned by the TAs. Project, there will be a final project. Basically, that includes a midterm proposal, final presentation, and a final report for a team up to 3 people. And for students that take this as 0 credit and pass long pass, there's no final project. However, if you're from SLAE, if you want to help participate, you're welcome to attend the midterm proposal sessions and also see any of the team. If they're working on something related, interesting to you, you'll feel free to join to help, all right? But this time, you don't have to take finals project. All right, any questions? Any questions regarding the course? Anyway, we'll also, by the way, we're going to have a WeChat group, right? I think that's probably the most efficient way to reach everybody, and have a WeChat group about this course, and we will make timely announcement and any updates. So check the WeChat group and also the book website frequently, and also that of course HKU student check the Moodle website frequently for latest information. All right, let's get started. So last time we talked a little bit about, right? I mean, intelligence is the very fundamental subject. It's probably, in a sense, it's probably, as I mentioned, right? It's probably the most important topic. It's what life is all about, right? Intelligence is a mechanism behind the life. I mean, there's a reason, right? So the existence of life very much depends on intelligence, right? So let's learn a few things. As I said, if we wanted to be interested in machine intelligence or so-called artificial intelligence, we better understand intelligence, right, in nature, because that's what we learn, what intelligence is all about. And as I mentioned last time, right, not everyone, but most people has very little concept or clear understanding what it is. Although everybody believes they understand about intelligence, right? But as a scientific subject, not quite so. It's actually, intelligence is also old, but also very young topic. So like we mentioned last time, right? The objective intelligence is really the animals or human try to learn what is predictable of the external world from the data they sensed, right? And most of the time we know in animals, right? Animals learn how to predict the world through correlations. Right? They see things are correlated, right? The most famous conditional reflex, right? Pavlov, right? Pavlov, right? Experiment, right? You can train dogs, cats, animals learn. If things are associated, related to each other, they start to memorize those, right? And this is the first, observation, some of the early observation about how animals learn to build a model of the world, right? To memorize useful things for their survival. Now, of course, it's not just about the food, right? It's a lot of everything, right? I mean, we work in this world, we live in this world, we interact with it, the environment, right? I mean, the world is not entirely random, right? Hence, there's a lot of things worth memorizing. And for example, the weather, tomorrow's weather. The reason we don't have in-person lecture because the weather is bad, right? So we actually forecasted it, right? We got a warning yesterday. So that's why we know today there's going to be a typhoon and so on. And hence, in generally, we learn how to predict events in the future, learn the sort of the trends of the weather. Also, right? You don't have to be, no physics to play soccer, right? And animals, again, you throw an object, they can actually catch it. They can actually predict the trajectory of the object pretty well, right? And of course, since ancient time, since ancient civilization, everybody is interested in objects around them, trying to predict how they move, how they, one of the most important objects that moving around us is, of course, the planets, right? The stars, suns, and so on, right? So ancient civilization, actually early science started with trying to study, try to predict how planets moves around Earth, around suns, and so on, how the stars moves around us, right? So that's astrology, horoscope, 黄历, right? 中国人的黄历, and then later on evolve into astronomy, right? So on. So you can see that a lot of early days, right? Animals, even early are, it's very, very empirical. We observe, we try to build some kind of model, memorize something from past experience, right? Try to predict the past, right? Through correlations, through periodicity, right? In the events. And then later on, right? We become analytical, right? From empirical start to moving towards, right? From empirical science to move to modern science, right? How to predict the model, motion of the object, say a planet, analytically, right? People start to formulate using mathematical language, right? As we talk, much more precise, unique language to specify how to predict the motion of the object, a planet, for example, right? Starting with Kepler's law of planetary motion, right? First law, second and third law, and how the planet moving around the sun, so on, as an ellipsoid, including the speed and the distance and so on. And as you can see, this is fairly interesting, right? So Newton's law says if the object has low force on it, 一个不受力的物体, right? Moving on a straight line. But actually planet move around the sun in ellipsoid. Hence meaning that they do have forces, right? It's actually ellipsoid. It's not arbitrary. It's a beautiful curve, right? That says a lot about the predictivity we're trying to learn about the world outside. Of course, Newton formulated it with the help with calculus, right? And formulated how actually object moving under the influence of sun, under the effect of force, right? Without force, you travel on a straight line at a constant speed, and with force, it affects its acceleration, right? F equal to ma. Of course, third law means that the forces are mutual, right? Exerted between objects are mutual. For example, gravity, the attraction of two masses actually have this equal forces given by the formula he formulated, right? The famous gravity formula. And this turns out, if you start with Newton's law, you actually can derive Kepler's law, right? At least among two bodies. Three bodies is a little bit complicated, but the two bodies can actually derive why a planet move around the sun as an ellipsoid and follow the first, second, and third law of Kepler, right? So you can see actually derive Kepler's results, law become results if you take Newton's law as the first principles. Now, of course, we go that, right? This is ancient time. Later on, people pick up the practice and really start to develop a whole rich set of science around it, right? There's many, many other phenomena, all the physically feasible phenomena around us, right? And they're at all different scale, space, and time. For example, at a very, very high speed, Newton's mechanics is no longer valid, right? It becomes relativity. if at a very large space scale, then you have to general relativity at the scale of the universe, right? Planet and so on. You have to use the general relativity. Or if you minimize, if you scale the space down to the microns, right? To the atoms, and so on, then you start to reach the quantum, real quantum effects, dynamics, quantum mechanics, right? So it doesn't really matter, but you know that, right, almost all physical phenomena we know today, so it sort of belongs to one of those so-called 17 equations that change the world, right? Of course, the majority of them actually are equations describe physical phenomena, right? Magnetic, Navier-Stokes equations, fluid dynamics, and how Schrödinger's equations describing the quantum mechanics, and so on and so forth, right? And so this is actually the interesting thing, right? As I mentioned to you last time, right? You see, in fact, we say 17 equations is not exactly right, right? In fact, one of them is inequality. It's the second law of thermodynamics. It's inequality. The entropy of the world, of a closed world, always increase, right? This is only inequality. The rest are all equalities, right? We told you why, right? Because every equation, in terms of if you have a phenomena in the high dimensional space, every additional equation allows you to reduce the dimension by 1. Okay? You are actually, hence make the event in the high dimensional spaces more predictable, right? So you restrict the solution, enforce the solution to be on the lower dimensional space via equations. Each equation add one more constraint, and so on and so forth. Right? Hence, it's arguably true that, right, even the whole universe, right, is live on a 10-dimensional model based on the string theory that unifies almost everything we know so far about the physical world, right? And one of the tools, of course, it uses the Calabi-Yau manifold, right, as one of the mathematical apparatus to unify all this quantum, general relativity, and so on, forces, all the 4 fundamental forces. Anyway, as you can see, right, it's amazing, right? Everything happened after Big Bang, can be described as just a merely 10-dimensional space, right, model. But I can tell you, right, 10 dimension is extremely large, right? There's a lot of variability already in a 10-dimensional space, right? That describes the diversity of the universe already. It's sufficient to generate all the possible phenomena, rich phenomena, diverse phenomena you saw here, right, in this world, right? So don't underestimate sometimes we say low dimensional space. Don't ever underestimate even a dimension as low as 5 to 10 or 20. The richness, what could happen in such a space is unimaginably complex, okay? Could be unimaginably complex, right? Now, so mathematically, right? So the intelligence, and in terms of memory, in terms of learning what's predictable, what's correlatable, that a universal ubiquitous mathematical property is that all predictable information we try to learn is actually can be encoded as a distribution, right? Data, right, is distributed in a way on a support of low dimensional. So those observations could be very high dimensional, like images, like all the things happening around you by sound or touches and so on, right? But nevertheless, right, those data, they're distributed around the extremely low dimensional support, right? Idealistic could be a plane, could be a mixture of planes, and could be a mixture of manifolds, low dimensional manifolds. And by the way, the numbers you probably don't know. And the dimension of each components may be different. Some subspace may be 5-dimensional, some may be 10-dimensional, right? And some are curved, some are simple, some are complicated, right? But nevertheless, compared to the ambient space, 对吧？在他们这个数据所 处在的这个大的空间、高的空间里面。Nevertheless, the physically plausible data, the useful data, the natural data are only situated around some extremely low dimensional structures. We call them, yeah. That's actually the distribution. So why this is useful, right? I mean, why we learn those? Once we get hold of those low dimensional structure, right? If we know those data are low dimensional, right? It really allow us, either we get hold of those distribution empirically or analytically, right? It allows us to do inference, so-called Bayesian inferences, because we have very good prior, which is the model of the world, right? Those distributions give us a model of the world. We can use it for Bayesian inferences based on partial noisy or even corrupted observations. For example, I can, if I know the distribution of X, which lies on, let's say, straight lines, if I observe Y, right? Observe a partial, maybe included, incomplete version of X, even with some noise, I can actually estimate, based on the observation Y, I can, can I have a pointer something? 这个好像没有 pointer, right? Do we have a pointer? Is this a pointer? No, that's annotator. Is there a pointer somewhere? Oh, spotlight. No, is the spotlight? Oh, can you see the spotlights, guys?
Oh, right. We can see.
The red dots, right?
Right.
Okay, perfect. That's great. So otherwise, I'm going to lose you. So basically, see, if X has the distribution, we know its distribution, extremely low dimensional. Now, if we see Y, which is maybe broken line or something I'm missing, and we can actually, based on the partial observation, we can already know what the X should be, right? Allow us to do complete data. So these days you see the generation, right? A generative model precisely use this fact, right? If I get hold of the distribution of X, I can generate, complete the image or complete the sentence, right? If I say a long enough context, that's exactly doing this. And also, right? It allows you to denoise. So for example, my observation Y could have some noisy information around it, right? Allows me to correct if I can get hold of what X should be lying on, I can do the denoising, making a noisy signal clean, right? We do this all the time, empirically or analytically. We'll talk about this more. Or sometimes we correct errors, right? We may see a piece that is corrupted, right? Some pixels are completely corrupted, right? Some by tampering, some by because even adversarially, people try to hide something, right? Crop something, right? So, but nevertheless, see, our eyes are very, very robust to those corruptions, right? So we can correct if we know what the data should be. So we can correct those errors. We do error correction. This is called robust recognition, robust. 所以就叫鲁棒或者稳健的 estimation in Chinese, right? So this is why our prediction decision can be very, very robust. 一个很稳健，即使有些偶尔会出错，对不对？我们都能知道 because it violates what expected, right? All right, so this is the Y low dimensional model. In fact, our brain, right? Our vision system, our brain actually follows, right? Precisely try to represent the visual, let's say visual input as complete as possible, by activity in a few neurons as possible. Basically, our brain is actually some of the most famous or popular model how our brain try to interpolate in the observed data, basically trying to representing the input, let's say Y, through some linear compilation of neuron activities. Right, this is a famous model or sparse representation model, right? Started with Barlow in 1972, and later on by people like Oshausen and Field. Oshausen is a professor at Berkeley, right? And Field and his advisor, I think it's from Cambridge, right? They're actually doing this, that how do I interpolate my observation as a sparse linear combination with a few fires of neurons, each AI representing, let's say, a prototype by some neurons, right? If they fire, they will generate this pattern. So you want to generate in this full picture with as a superposition, a few as possible superposition of the patterns so that to interpolate in the image, right? Hence, it's very sort of low dimensional, try to representing the phenomena with very low dimensional models. It will be more specific there, right? Hence, as you can see, the structure, the predictive structure here, I draw straight lines, right? Of course, the low dimensional structure may not be just straight linear, but the linear ones are the easy to understand. See, historically or even intellectually, right? We know the brain process is not linear, right? But nevertheless, linear model usually is a good starting point. Analytically, also it's actually at least a good model to approximate if the nonlinearity is not severe, right? If its nonlinearity is benign, 那个比较温和的非线性，我们可以用线性的模型去近似 right? Now linear model is always a good start to approximate what we're studying and also to capture the essence. So if we have some observations, right? Let's say we have some measurements, and we have some, we try to have fit. We see at a certain A, we see, giving some input, right? We see the response is Y, right? Some signals, right? A is variables. When A variant change, Y will change its value. But how do we find if I see a again, how do I predict the value of Y? You see some new A, how do I predict the value of Y, right? This is a very classical question, right? If I see A again, what is the new value of Y? A new A again, what is the value of A? So of course, the most simple class predictor we can build is assuming the function f is linear, right? Differ from, it's just a linear combination weighted of those variables A1 to AN. Right? So weighted sum of those A1 to AN. So the rest is just to find out what those X are, right? In order to predict, right? If I know X, give me a new A, I'll be able to find what the Y is. Now, how do I find X? All I have to begin with is some samples of the paired samples AI and YI, right? So then the question is, how can I solve this equation? If I have enough of those measurements, pairs of AI, YI, I need to find the X, right? Satisfy those equations. Okay. So of course, the measurements, the YI, in reality, is not going to be very precise, right? Could be corrupted by some noise, small noise, or even some outliers once in a while, sparse outliers, right? Some errors. Most of the time, maybe it's clean, but once in a while, YI gets corrupted, right? This is the kind of two types of typical corruptions, dense noise or some kind of sparse errors, right? So you should anticipate that. So our job is to try to solve for the best X given enough pair of AI, YI. Get it? Right. So this is a very classical problem, by the way, right? And you try to use a linear function to regress, Y with A, right? This is called also a linear regressor. Classical question in signal processing in statistics, okay? There's a long history, right? All the famous people are interested in it. Starting to say, you can see this is 18th century, right? A few hundred to 300 years ago. Gauss, Legendre, Gauss, Boscovich, we'll talk about it later, and also Logan. And those are famous people, have all studied this, a long, rich history, how to estimate, find its function X, despite error correction, noise, errors, and so on and so forth, missing data. So here's a story, right? You can see, actually the story is kind of unexpected, right? You can see everybody probably, whenever you see this problem, many of you learn in high school or even in college, is how to find X, use least square, right? That's how Gauss, assuming the noise is a Gaussian distribution, and you minimize the two norms, right? Y minus AX You build up the AI, or this AI build them into a matrix form, to make this a stack of the vector. This is where linear algebra and matrix become very popular, very useful, right? You stack all your measurements, the M measurements in the matrix form. This is essentially the L2 norm between the vector Y and AX, right? You try to find X that minimizes this L2 norm, right? And given that if the noise is Gaussian, the L2 norm is exactly the solution, exactly associated, is exactly is a maximum likelihood estimate for X. Okay, so both geometrically, statistically meaningful solution. So this started, everybody attribute to Gauss, but actually the story that's actually wrong. Legendre is the first one proposed it. But actually, there's something with someone else. There's a very interesting story. Before Gauss, least square, actually the people, when they first look at this problem, Boscovich, this is about half a century before this guy, proposed to do L1 minimization. So minimizing the absolute value, difference between the absolute value, between the predicted value and the observed one. Okay? So turns out what Boscovich had in mind is not this picture, it's actually this picture. So he's worried about the sum of the equation. Most of the equation is okay, but sum of the epsilon is non-zero, right? So he actually suggests L1 is better, right? But now why everybody works on L2? So you should read the chapter Appendix A, right, of linear algebra of my previous book, right? Because least square has closed form formula, has closed form solution. L1 does not. You can only solve this one numerically, right? That's why people have been practicing least squares for 200 years, and nobody cares about L1 minimization until very, very recently, okay? We'll talk about that in a second. About the 1960s, people start to realizing the importance of L1 because they wanted to dealing with the errors, that is high frequent errors. So this is actually Ben Logan, his PhD thesis in the 1960s, actually revisited L1 minimization, got a very surprising results, but I won't get into detail. That's actually in the, if you're interested, you can read my other book. Now, so there's many different variabilities of this least square, right, regression. This is just assuming the noise is, first of all, the noise is Gaussian, and also X could be anything, right? In practice, people normally have some constraints on X. They don't want the X to be all zeros, or all non-zeros. They don't want the X to be free. Very often, they want to pick, as few A. X is only take as few columns of A to regress Y. They don't want to use all the A's to regress. So this is exactly inspired, for example, that's what our brain is doing, right? If we see a picture, we don't want all the if we use all our neurons, of course we can regress the signals very, very well, but that's very wasteful. We want to use as few neurons as possible. We want to use as few regressors as possible. Can we do that? So that actually turns out, how can you select only a few rows of A, columns of A, right, to regress the Y, right? Or make X, this is also best subset selection. Just pick X that non-zero entries less than K. You're only allowed to use K columns of A to regress Y. So what's the best solution, right? It's 1960s, people are starting to be interested in those problems. And in 1996, about 1990s, people say, okay, L0 norm is this is very hard to solve because you have to find all support of X, right? How many possibilities? If X is n-dimensional, there are K entries are non-zero. That's n choose K, right? That's exponentially many possibilities. 就是组合数嘛，对吧？ N choose K. So of course you can do this in a brute force way, but when N and K are large, it's hopeless, it's intractable, right? It's NP hard. Then 1990s, people start to interest in this again. Say, let's relax this L0 norm to L1 norm. And again, this gets revisited And you can see that 1998, people start to do the basis pursuit, and many famous people start joining, including Americanus, Terence Tao. Everybody works on, in late 1990s, everybody who's who in mathematics and in applied mathematics is working on this problem. So that actually leads to the so-called compressive sensing revolution, right? That's first century, first decade of the century. It's very much everybody working on, as I said, before neural networks hits fame, everybody works on compressive sensing, including Yang LeCun also, everybody works on this. How do we solve this inverse problem that find a few non-zero entry of X such that we can regress the data, predict do the least-square, do the regressor, find a regressor that can predict the signal well, right? Also make this robust and so on. Also sometimes dealing with nonlinearities. So if you're interested, this gives you the connection to, this is my entire previous book is about this topic. So there's something very interesting, right? See, the first decade, 就是这个世纪的第一个10年啊 people start to get into high-dimensional geometry because of this kind of problems, right? Even it's linear models, right? But even this problem looks simple, right? Banal, 同学们 the problem looks very, very simple, right? You're solving linear equations subject to some sparse constraints, right? Looks very banal, but actually turns out this is one of the hardest problems computationally, right? Because it's NP hard, and it's even harder to approximate. If you're interested, you can read the book, right? And so in the beginning, people are very pessimistic, right? Meaning that we cannot, there's no tractable or scalable solution to solve this class of problems, okay? 大家知道对不对？现在数学 this remains as an open problem, right? If P equal to NP, right? So this is actually NP hard problem. And also it's an important one, it's a very useful one, right? People solve problem of this kind all the time. Hence, this is one practical problem, really makes the study of P equal to NP or not equal to NP very, very important, right? It's not just theoretical importance, because if we can understand, right, P equal to NP, tractable versus non-tractability, we're going to affect solution to this class of problems. That's why in the first 10 years of the century, everybody who's who in applied mathematics works on this problem. 明白吗，同学们？就是不光是应用上很重要，而且它的理论上极其重要。Right? See, guys, for people like Tao Zexuan, right, Terence Tao, right, there's only very few people, very few problems he cares about. I'm pretty sure Riemann hypothesis and P equal to NP, those are the two problems that he's always pay attention. Okay, whenever there's some progress, some chance to tackle them, he will jump in. Right, the same should you. Right, but nevertheless, in the first 10 years of the century, right, there's many brilliant minds work on this problem. They start to get, because you want to solve this problem in the extremely high dimensional spaces, right? 当这个变量很少，所以这个问题不难，对不对？哪怕这个 exhaustive 这个 brute force 能解。The problem is the NP hard problem is when the dimension gets high, right? So now actually turns out that in practice, you do want to solve the problem in the very high dimensional spaces. Turns out there's some very, very big surprises, right? Turns out this class of problem actually can, under very banal conditions, this problem is become no longer NP hard, right? So you actually can get a very efficient algorithm for correct solution under very, very banal conditions that actually become the theory, right? So it start to allow people to understand high dimensional phenomena for the first time. Right? At least for engineers, mathematicians know those things a long time ago. But for engineers, especially for computer scientists, it's actually the first time people realizing there's a lot of amazing phenomena in high-dimensional spaces that were not harnessed or exploited for efficient computation. 就是这高维空间几何, right? It's very, very different from the low-dimensional geometry. Right? For example, there's a lot of interesting phenomena, right? Example, right? 就是这个叫 measure concentration. 大家都知道，对吧？比如说 if I tell you, 大家都知道一个二维的球面 ，right? A two-dimensional sphere, 它的这个 area 是基本上是均匀分布，对不对？Now if you think about the sphere in the n-dimensional space, when n is high, 好吧，都不要很高 ，n 大概到30、50啊，就是50维空间中的一个 sphere。Turns out almost 99% of its area is concentrated around the epsilon band around the equator。这很奇怪，对不对？就是说你在这个50维的球面上，它99%的 area volume 是集中在它赤道附近的一个 epsilon band 上面，之外是几乎没有 area 的。Surprise, right？而且随着维度 as long as n 的 n goes high， 这个 epsilon 变得越来越小。这还不是最神奇的地方，最神奇的地方是99%的 area concentrated on any 赤道，任何一个赤道。你可以画一个跟这个赤道正交的方向，也是99%的 area concentrated around that 赤道。Can you imagine that? Can you visualize that? 对吧？所以在高维空间中出现的一些现象啊，让人你要是脑袋想爆了你也想不通这就是，但是这是 mathematical facts， very very surprising, very very interesting， 对吧？好，另外一个现象，我只是举2个例子Another example is called 大家都对高斯分布很感兴趣，对不对？都觉得自己很熟Gaussian distribution， 大家都知道，一维的高斯像什么这种，对不对？一维的高斯就是大家都知道那个 bell-shaped curve，right？ 这个 density is like a bell-shaped curve，right？ 大家知道吧？那么你中间的是the more close to zero, the mean, the higher the density， 对不对？中间的密度高。旁边的密度低，对不对？那2维的高斯大家也知道，对不对？也是 ，if you sample from a 2D Gaussian, usually get more points in the center, right? The scatter around outside. Well, turns out in high-dimensional spaces, if you have, let's say, 500 dimension, a Gaussian distribution, a generic Gaussian distribution, right? You sample, let's say, 5,000 points. 比如在500维空间中的高斯。你采5000个点或者1000个点，好吧 ？Clear， right？ Then turns out 很神奇的事儿，这5000个点没有一个点在里面，它全部在这5000个点可以 span a convex hull， 一个凸极，所有的点都在外面 ，all the points outside actually span a convex hull，right？ 这还不是神奇的地方。这些点，你把它，你看任何2个点，对吧？2维图像上，如果我们把2个点连起来 ，if we draw a line between any 2 points, right? Those lines going to be cut across, right? 是不是？对吧？这个凸极这2个点是不是会进到这个凸极的里面去，对不对 ？In the high dimensional space, that doesn't happen either. Turns out you can draw an edge between any 2 points. 那个 edge stays on the outside. So there's a lot of very weird. So basically, again, the Gaussian points actually again concentrated on a sphere. Right? It's very very interesting. I mean, actually, people didn't anticipate this, right? There's a lot of, but it turns out that those phenomena precisely can harness for efficient computation and solve all the hard problems like this ones. 好。But anyway, so this is about fitting a linear regressor, right, to y, essentially solving linear equations, even those a's are given to you, right? And x is y is vector, a is vectors, and you try to regress them, right? But in many practical situations, the regression has taken some special form, right? 有时候不是这个 batch processing. Many in the real world, our prediction, the regression is actually causal, right? It depends on time, right? It's kind of is a function of time. So those vectors, those structures, this data has very special structures, right? They're evolving as a function of time. So again, we try to, if we have observation, z is the input, x is the output. We wanted to estimate what is the regressor. Y, H is actually regressor acting on those input. Usually this is take a 卷积, right? This is estimate a linear time invariant process using this kind of convolution equation to describe the prediction, right? So x is the linear time invariant response of some input sequence z. 里面如果学过信号系统的学生 if you have learned signal processing, this is the very simplest class of models, right? So it turns out that during the war, 维纳就是我们上节课提到的维纳，那个 Robert 维纳，his job is precisely assigned to predict the how to shoot airplanes with the cannon, 就是高射炮打飞机。Then in order to do that, he needs to estimate the trajectory of airplane from the radar on the ground, right? So you can see that the x may be, right? Z may be, x may be the trajectory of airplane. Z may be the input of the angle of the 高射炮, right? You want to find out what are the, h so that you can predict this actually can actually shoot the gun so that you actually hit the airplane with high precision, right? So this become a temporal estimation problem, right? How do I find h such that the predicted trajectory is closest to the observed x, right? Minimize the mean square error, right? So he actually derived a solution to this, right? Essentially, it's very similar to this problem, by the way. Very similar to this problem, but it has this special temporal setting, right? 这些信号 a 和 x 变成了变成时间的函数。So it's more special, but essentially mathematically it's the same class of problem, right? Find the h to solve this problem, and he actually derived the famous Wiener filter for this class of problem, right? And of course, this takes different forms, has different variants. But if you wanted to know this class of problem, the read appendix I posted as homework, right? There is a very careful derivation for more general forms of the least square variance or least square estimators or least variance estimators of this form 维纳律波所以你看最早的这些人，对吧？我上次给你们讲过，同学们，你们想想，对吧 ？Legendre 高斯最早关心什么问题？去噪的问题 ，OK？denoise 的问题 against the linear models。And 陶泽轩Amanda Candace care about again 去噪的问题linear regression 的问题有时看似简单的问题，往往也是会很难的维纳，我们的 machine intelligence 的真正的 father of machine intelligence。OK， this is undisputable。OK， 现在大家经常记，现在这些人，我觉得现在人动不动就是这个 godfather， 那个 father 那个妈妈，那个，这都是完全是对历史是完全不尊重同学们好好的把历史搞清楚这连祖宗都不认识了所以你的学问肯定做不好同学们。真正的 I think the true father of machine intelligence is Wiener, undisputable, Nobel winner. And actually he started with denoising problem for simplest class problem, of course.